pleasure to introduce Dr. Claire Nichols from the University of Oxford. So Claire did her PhD up until 2017 on tiny space magnets, and then went to MIT to a famous boundary magnetism group there, and stayed there until 2020, when then she was appointed associate professor at Oxford. And Claire does, really works at kind of three frontiers, I would say, of paleomagnetism simultaneously. And obviously, this is one of them, lunar magnetism. The other two, I think you're going to mention in the slide now. So, yeah.
Brilliant. Thanks very much for the intro, Andy. And thank you very much, everyone, for being here. So yes, as Andy says, this is kind of one of the things that I do. So today I want to talk to you a little bit about the moon and the lunar magnetic field, and kind of explain to you why this is a big headache for all of us that are interested in planetary magnetism. But to start with, just a little bit of background about kind of the sorts of things I'm interested in. So I basically I'm a paleomagnetist. So like Andy, I like to stick rocks in machines and figure out what was going on with the magnetic field in the past. But I also dabble in kind of a bit more kind of rock magnetism, so really understanding why minerals are magnetized the way they are. So I do lots of high resolution microscopy to think about that. And I also do field geology, mostly because I like going to very cool places. And so that allows me to kind of work on these three big questions. So I'm interested in Earth's magnetic field and the very early history. So kind of way back into the Archean of what the magnetic field was up to then. I think about the lunar dynamo, which I'll talk to you about today. And then I also, particularly for my PhD, looked at meteorite magnetism. So trying to understand kind of what asteroids are up to and what they're doing, generating magnetic fields. And the reason that magnetic fields are a really, really good and interesting way to think about lots of problems in planetary science are because they tell us about the thermal history of a planet. They tell us about differentiation processes. So the idea that you're forming a metallic core surrounded by a silicate mantle tells us about deep Earth processes once you have that core. So what's going on around your core mantle boundary. But then on the surface, it also allows us to think about things like atmospheric escape and how magnetic fields influence that kind of thing, and habitability. So do we need a magnetic field in order for a planet to host life, which is really useful when we're looking at exoplanets and that kind of thing, and trying to figure out where we might find life elsewhere. So there's lots of very, very kind of big questions that we can think about to answer these questions using magnetism. And really, it's all underpinned by this idea that planets generate a magnetic field in their metallic liquid core. Okay, so you need to have at least part of your core to be liquid. It doesn't matter if it's the outer core like Earth or if it's the inner core for smaller bodies where crystallization happens the other day. But you need some liquid metal that you can mix very, very vigorously in order to generate a magnetic field that we can see at the surface. And planetary rotation sometimes plays a big role in that, and that will come back into my talk a little bit later about why the moon is particularly difficult to explain. Okay, so this talk is in three sections. I'll start with a bit of a background as to why the moon is our problem child. I'd say it's up there with Venus in terms of giving us headaches as planetary scientists. Then I'll talk about some work that I did mostly when I was a postdoc at MIT, thinking about the shape of the lunar magnetic field and seeing if that kind of helped us to understand what was going on. Spoiler, it didn't. And then I'll talk about some work that I've been doing in the last couple of years, thinking about kind of a completely new mechanism that might be driving a magnetic field within the lunar core that doesn't just depend on kind of the convection being sustained. So that will be my final take home, and you can decide if you buy that mechanism or not. Okay, so why is the moon so difficult? What is the problem? So the moon does have a metal core like Earth, but for Earth, the metal core is very big. It's about half the radius of the planet. For the moon, it's only 1/7 of the radius. So the lunar core is teeny, teeny, tiny. And everything we know about how planetary dynamos are kind of driven implies that that means that it should generate very weak fields because it's a very long way to the surface, and that core should crystallize very quickly because it's not very big. There's not a lot of metal there to make solid. So if we knew nothing about the moon's magnetic field, we would guess that we would get weak fields for a short amount of time. That's kind of intuitively what we would expect for a body with such a small core. So I'll now show you what we actually see. So on this graph, I've got paleo intensity. So that's basically how strong the magnetic field is on a log scale on the y-axis. And then I have time going back from the present day to the start of lunar history. And so just for those of you that don't think about magnetic fields very much, the Earth's magnetic field basically sits in that blue region. That's the magnetic field that we experience on Earth today. Okay, so we would expect the magnetic field on a much smaller body with a smaller core to be weaker than this. And this dashed line at the bottom is basically the absolute weakest field that we think we could say is being driven internally by planets. If it's any weaker than that, then it's probably things like the solar wind is an external source. So we're imagining for the lunar dynamo, it's going to sit somewhere between these two regions. And this is kind of a compilation of most of the paleomagnetic studies that have been done. So this is looking at samples collected during the Apollo missions, bringing them back to Earth and measuring them using a magnetometer in various labs. And immediately you can see we've got quite a big problem on our hands. Okay, so for the very early record, we're actually getting magnetic field strengths that are even stronger than Earth's field today. Really, really strong and for quite a long period of time. So we're seeing probably for about 500 million years, very, very intense magnetic fields are generated. Here, the error bars are massive, but nonetheless, we think we are getting a field. It's just weaker. Then we have this one disk point on its own with a very poor age constraints. And then finally, within the last billion years, we have two magnetic fields that are very weak. So we're pretty confident the lunar magnetic field had turned off by about 1 billion years ago, was extremely strong in its early history, and then there's a middle period where we just don't have many observations, so it's difficult to say very much. So I'm mostly going to be focusing on that early, very intense period of magnetic field generation and trying to figure out how on earth can the moon generate fields that strong. And I'm not the first person to think about this at all. Lots and lots of people have been working on this for a long time. So this is a paper that came out in 2018 by a guy called Alex Evans, who is a professor at Brown. And what he did was he was really generous to the moon. And he basically said, if we give the moon the best case scenario of generating a magnetic field, we give it absolutely unrealistic amounts of energy. Okay, so we're going to make the moon super radioactive, so there's loads of heat. We're going to have lots of gravitational energy, lots of latent heat crystallization. What's the strongest magnetic field we could possibly generate in the best case scenario? And this red bar here is the strongest field you could generate for that period of time. So it's not strong enough. And that's unrealistically strong anyway. And if we need to sustain a field all the way through lunar history, right, until 1 billion years ago, then actually the strongest field we can generate is about 2 microtesla, which is way weaker than everything we're measuring. So there's a fundamental problem between theoretically what we know about the energy budget of the moon and the observations that we're seeing from the paleomagnetic record. There's a big discrepancy that we have to deal with. The story has become even more complicated in the last few years because another group have now started working on these Apollo samples. And so I'm showing you basically this is the same paleo intensity on the y-axis still and going back in geological time on the x-axis. And they're basically saying these measurements are all wrong. Actually, everything has no magnetic field. The moon is not magnetic at all. And the only time they say the moon could have a field is in this red period in its early history when the impact flux is really high. So they're saying there is no lunar dynamo, you have lots of impacts early in the history, that might generate a very early magnetic field record on the lunar surface, but after that, there's nothing to see. Okay, so we now have very discrepant measurements from lots of different lab groups. The story gets murkier and murkier. And another problem is if you look at the crustal magnetic record of the moon, okay, so this is basically how strong a crustal magnetic field you see if you image the surface. So on this color scale, all the blue colors are basically not magnetized, red colors are magnetized, and this is the front and the back of the moon. So actually the vast majority of the lunar surface isn't very magnetic. This doesn't support the idea that you have these strong, sustained magnetic fields that we're seeing when we measure these individual samples. And so if you try and put that in context of the paleomagnetic measurements, They know the relative age of these magnetizations by crater counting. So you know if you have craters in other craters, you can work out the relative age of each one. So it's only the very, very oldest craters that formed before 4 billion years ago that are magnetized. And those do have a similar magnetization to this early history. But everything after this point, the crust implies there's no magnetic field. So we have a quite good set of observations for the moon. We just don't have any idea how to reconcile all of these different observations that we have. This is a really, really big problem for us. And so when I first started working on lunar samples a few years ago, something that hadn't ever really been done was thinking about the shape of the lunar magnetic field. Okay, so we know the Earth's magnetic field, we have a north magnetic pole and a south magnetic pole, and we have big field lines that loop round. Okay, so it looks like a bar magnet. We have a dipolar magnetic field. And that is partly because of the rotation of the Earth, which is aligning the convection cells in the core into kind of stable patterns that give us this nice dipolar signature. So if we can work out what the shape of the lunar magnetic field looks like, that's something that we can put into models, and that might help us to understand the kind of mechanism that's generating the field. So it would be a useful extra observations. And so I looked at a couple of samples that were collected from the Apollo 17 mission. So all the Apollo samples have a five-digit number associated with them, and 7 basically means that it was collected in the Apollo 17 mission, so the very final manned mission that went as part of the Apollo series. And these rocks come from, they're 3.7 billion years old, so they're from that early high intensity part of the magnetic field history bit that's very, very difficult to explain. And these were not really thought to be remarkable samples. People have characterized them petrologically. They haven't been measured paleomagnetically, but they weren't thought to be really any different to the other samples until a much more recent mission, which launched a camera into orbit around the moon. So the Lunar Reconnaissance Orbiter camera took incredibly high resolution pictures of the surface of the moon. And that gave us new context into actually what we were looking at with these samples. So the Apollo 17 mission, where these samples were collected, is the only mission where they sent a geologist to the moon. Which really shows that, you know, it was all about the space race. They weren't actually very interested in the science they were going to get out of these samples at the time, because it was a very last ditch, oh, okay, yeah, we probably should send someone who knows something about rocks at least once. So Jack Schmidt was the only astronaut who had a geology degree who was sent here, and he has remained very, very active in the research field. So he is still constantly going back and trying to learn more about those samples he collected. And so they landed at this site here in the Apollo 17 mission. They basically were working in this area, and the samples that we're looking at come from the Camelot crater here. And so once he got all this high resolution imagery, he then looked back at his field notes essentially and made new interpretations of what he was looking at when he collected the rocks. So at the time when he was there, he assumed that he was sampling from a fresh impact crater, okay, which looks something like this. So you can see all these pock marks are essentially where a ejector has been thrown out of that impact crater. So he assumed everything that he was picking up was just kind of loose rock that had been flung some distance by the crater. So he thought there's no way we're going to get orientations out of any of this stuff. And so this is just kind of a hypothetical cross-section of what he thinks he's dealing with here. Okay, so you basically have this brachiolens. So everything that you see on the surface is ejected material. There's nothing in situ to look at. But in fact, when he got these new images, he found that the crater did not have the morphology he expected at all. Okay, so here it has very, very sharp features. Okay, you can kind of see this sharp inner rim and this outer rim and all of this ejector. And actually, in reality, Camelot looks like this. It's much smoother in terms of its topography, and there's much less of this ejected material, obviously, on the surface. So that led to the reinterpretation that actually what you're dealing with here is a crater that's undergone a lot of mass wasting. We don't have erosion on the moon like we have on Earth. But what that's done is it's meant that actually a lot of that fresh material has kind of sunk out of the way, and you're beginning to expose potentially in situ material, okay, so bedrock, for want of a better term, around the surface of this crater. So Jack realised that actually that might mean some of the samples that he collected are really valuable because they might actually have their original orientation. And so most of them are still very obviously loose breccia, but a few of them come from outcrops like this, where they actually hammered bits off blocks. And so here we think this block has probably been rotated, but you can kind of see these planar features running through it, which we think are telling us about the paleo-horizontal. Okay, so this block is probably not exactly where it landed, but we now think it's not very far from its original position, and we think we have indicators that we can use to tell us about the paleo-horizontal. And this is basically based on what we see with basaltic flows on Earth and thinking about how things like viscosity and flow behavior will change in much lower gravity on the moon. We think these are essentially vesicular horizons that are causing these planar features in the rock. So it's a reasonable assumption to think that these were horizontal when they were first in place. And so we can then actually look at where they hammered material off this outcrop, and we can compare it to what we see in the lab. So the really cool thing, when they brought all these samples back to Earth, they spent an awful lot of time photographing them in the same light conditions as they were sampled on the moon. So this tin foil is not here because it looks cool and sciencey, it's actually to make the lighting exactly the same. And that's really useful because what it means is we can compare every little shadow and pockmark on that sample to all the photos that the astronauts took when they were on the moon. So I can kind of guide your eye to some features here because it's not easy to pick out to start with, but I think you can start to see the sorts of features that we can see on both. And so really what I spent an awful lot of time doing was essentially trying to do remote astronaut field geology to figure out the orientation of this rock that we had compared to where it was on the lunar surface. So I looked at all of the photos that they took and all of the logs. This is all freely available online, and actually they're well worth a look through, kind of the transcripts of all the conversations they had when they were on the moon. Astronauts certainly have a sense of humour. And so they took a whole bunch of photos walking around this block, and I could use those to work out the orientation of the block on the lunar surface. These white bits are where they accidentally were holding a sample bag in front of the camera while they were photographing. There are some expletives about that. So they were not necessarily the most careful, but you can still see enough to do something with it. So with my structural geology hat on, I can take all those relative measurements as they walked around the block. I can plot them on a stereo net, and then I can recover the plane of those features in the position that they're at on the moon today. Okay, so I then know exactly how my sample is oriented on the lunar surface, and I can then untilt it, bring it back to paleo-horizontal, and say something about the direction of the magnetic field. So just to go through kind of what that actually looks like in terms of the lab work that we did. So we were only given a very, very small amount of this sample. Okay, so we were given this chip, and that's actually more than enough to do paleomagnetic work with. So normally, if you're looking at Earth rocks, that would be smaller than a single sample. So the cube here is 1 centimetre across the top. So this is a really, really tiny chip of rock. Usually that's the kind of offcut you just get rid of for a terrestrial paleomag study. But no, we meticulously mounted it in a known orientation. So this orientation cube, every time you do anything to the sample, you move the cube with it, so you know how you're looking at it. And we chopped it into teeny, teeny, tiny little cubes, and then we could measure each of those cubes individually. And that's really important in paleomag because we want to check that the magnetization in all of our subsamples is self-consistent. If they all tell you a different story, then you're not going to trust any of it. So you need to know that you're getting the same answer in every piece that you're measuring. So just prepping the sample is a lot of meticulous work when we're dealing with things this small. And then we make these horrible things called Zijderveld diagrams, which some of you are very familiar with these, some of you are probably not. I'm not going to burden you with how they work. But essentially what we do is we apply alternating magnetic fields that get increasingly strong. It's a bit like wiping a tape, for those of you that remember when that used to be a thing. And so we gradually remove the magnetization of the sample, and then we can essentially plot it as vectors. And so these arrows are telling me about the direction of my magnetization. So the squares are telling me about the declination, so whether my magnetization is pointing north, east, south, or west. And the circles are telling me about how the magnetization is pointing relative to horizontal. So how steeply dipping or plunging my magnetization is. So for each of our subsamples, we can demagnetize it and we can see what it remembers about the direction of magnetization at the time that it formed. And so we end up with a stereo net that looks like this. So we have unstable, low coercivity components. That's basically things that have probably been remagnetized. We don't trust them. We see they're very scattered within our subsamples. And then we see these stable magnetizations are all clustered. They all point in one direction, and that's very reassuring. That's what we want to see if we're dealing with a really stable paleomagnetic signal. And as I said, with this block, we don't think it is completely in situ. It's almost certainly rotated. So we ignore the information about declination. That's not, we can't say anything about whether the magnetic field is pointing north, east, south, or west because we don't know how much we've rotated. But we can tip everything back to being in the paleo-horizontal by taking those planar features on the blocks back into the horizontal surface. And then we have what we think is how steep the magnetic field was at the location of that block for each of our subsamples. And we get relatively consistent measurements. So we get a steepness of around 30 degrees. So that's the number that we really want to deal with, to then start to think, what does that mean for what the lunar magnetic field looked like? And the way that we can start to interpret it is because we not only now know the steepness of our magnetic field. Okay, so my black star here is my mean inclination, and then you see all my subsamples are relatively spread out, but we know our inclination is somewhere in this region. And we also know the latitude, so we know how far north we were on the moon at the site where we took this sample. So now we can think about different models of magnetic field generation and what kind of shape that would give us in terms of the steepness of magnetic field versus the latitude that we're at. So I kind of went through all of the literature back to when the Apollo missions launched and thought about all of the ideas people had proposed for the origin of lunar magnetism. So the kind of least bonkers one, because it's the one that looks like Earth's magnetic field, is that we have a dipolar magnetic field. Okay, so aligned along the spin axis, pointing north-south, it looks like a bar magnet. And for a dipolar magnetic field, we know very well how the steepness of the magnetic field changes with latitude. That's a simple equation, and we understand what that should look like. So that's our best case scenario, is it looks like Earth's field, something we can understand. Something that is more likely for a body like the moon, and I'll come to why this is in a minute, is that the magnetic field is actually multipolar. So rather than having just two poles, you have lots of poles everywhere and a much more complicated field morphology. And that's very difficult to predict exactly what it will look like, but essentially you will expect to see large variations in inclination with latitude, depending on how multipolar your field is. So I could draw any number of different squiggles there, and all of them might agree with a multipolar dynamo. And then I considered all the other ideas that have been proposed, including things like hitting the moon with a meteorite on one side of the body, and that actually causing plasma to be ejected out the other side of the body. There are some really mad things that people have thought about. But in every case, you can kind of think about how steep you would expect the magnetic field to be at a given latitude. So, for example, in this case, the plasma field is predicted to go basically vertically out of the lunar surface. So you would end up with a high inclination, no matter what latitude you're at, depending on if you happen to be at the antipode. So I basically went through and thought about what we would expect to see with latitude for every single one of these different scenarios. And then I can plot them all up on this diagram. So this is now kind of showing all the possibilities, and I can compare it to my data. And what we find, this was actually quite surprising when this dropped out at the end of having reoriented everything using the Apollo samples, meticulously measured all these tiny little cubes from the moon. Actually, it sits exactly where we would expect for a selenocentric, which is a fancy word that just means moon-centric, axial dipole. So basically a dipole aligned with the rotation axis of the moon. It's the exact inclination we would expect for the latitude that we were at. So that was kind of cool. And initially we were very excited by that, because if the moon's magnetic field looks just like the Earth's magnetic field, then this is a really nice, important observation that is kind of confirming we are dealing with a dynamo. Unfortunately, though, I then dug into some literature that people hadn't really considered in detail for the moon before, which is the fact that actually, if you look at lots of dimensionless numbers that dynamo modelers like to use to think about the behavior of dynamos, the moon sits in this red region, okay, which implies that it should be multipolar. So rather than being a nice dipole with a north and a south, you should have lots of poles everywhere. And the main reason that that drops out of dynamo models when you look at these parameters is because the lunar rotation rate is very, very slow, right? The moon is tightly locked to the Earth. The same face is always facing us, right? We only see one half of the moon. So if you think about how fast it's rotating, it's not very fast at all. Certainly not fast enough to align those convection cells to give you a dipolar field lines on the spin axis. It's really just not got enough spin for that to be the case. So actually, the fact that we're getting an observation that implies the magnetic field is dipolar is a really big problem. We've made things worse, not better. It's not the only planet, though, or the only planetary body that has this problem. So Mercury is another problem child in this case. So Mercury is also tidally locked, so it's rotating very, very slowly. And it has a much bigger core, so it doesn't look particularly like the moon, but it has the same problem of rotating slowly. But we've directly observed Mercury's magnetic field, and we know it's very dipolar. So clearly, there's something that can allow slowly rotating bodies to generate really nice dipolar fields. And this has been something that people have been thinking about for a few years now, mostly in the context of Mercury, but we think we can apply the same thing to the moon. And one idea, which is particularly appealing to explain the moon's magnetic field, comes from seismological observations. So this is what we think the interior structure of the moon looks like. This is based on, I think, 3 seismometers that the astronauts deployed on the lunar surface. So it's not the best coverage. And I'm sure lots of seismologists would have thoughts on this. But if we take the interpretation as read, then what they find is you have a small solid inner core, you then have a fluid liquid outer core, and then you have this mush zone at the base of the mantle. And the idea is that that mush zone can actually filter out the higher order signals in your magnetic field. So even if the core itself is generating a multipolar field, you end up only seeing the dipolar signal at the surface. And a similar idea has been proposed for Mercury. I'm totally agnostic as to whether that is a thing or not, but I think it's an interesting concept to think about. And so that really takes me onto the next part of the talk, thinking about actually other ways that mush zone might be useful for thinking about the moon. So we'll park the shape of the lunar magnetic field. That remains a kind of outstanding question as to why it looks dipolar. Does it really look dipolar based on our one observation? And if it does, what's that mush zone doing at the base of the mantle? But that then got us thinking about a totally different way of explaining the strong intensities for the moon in general. So there's a lot of research that's been done in the last few years thinking about kind of the origin of this mush zone at the base of the mantle, and thinking about kind of the dynamics of how the moon came to be the way it looks today. And so we know that the moon had a magma ocean just after it's formed in its very early history. It was completely molten, and it then crystallized, and you end up with a very, very dense layer of titanium-rich ilmenite-bearing cumulates at the top of the mantle. So if you look at the crystallization sequence, you basically end up with all this very, very dense stuff near the surface of the moon. Because it's denser than the material that sits below it, it's gravitationally very unstable. So people have basically looked at modeling what happens if you then hit the moon in this kind of gravitationally unstable state. So if you have an impact event, then they're basically proposing that you will trigger mantle overturn, and you will get this sinking. So this titanium-rich material is shown in green here, and you will end up basically causing that dense material to sink in diapirs to the core mantle boundary. So it will come down in big blobs over time. And they're arguing that that then ends up being your mush layer at the base of the mantle. Because thermodynamically, it's no longer where it wants to be. So it sinks, it then starts to melt, and you then have this layer at the base. So this has gained a lot of traction from a lot of different perspectives in the last few years of kind of how we end up with this layer here. And again, a study came out a couple of years ago where they started to think about if this could help with the idea of how we generate such strong magnetic fields. So this was a fairly simple study where they just did this back of the envelope calculations. And they said, if you drop some of this titanium-rich dense material to the core mantle boundary, and it then starts to melt, then you're going to be drawing heat out of the core. So you will increase the flux during that melting event for a short amount of time. So if we do that and we boost the energy available to the core by suddenly putting something compositionally different at the core mantle boundary, how strong a magnetic field could we then create? So they basically looked at how much titanium-rich material that you sink in one go. So this is basically how big a blob we're dealing with, and then how long that blob takes to melt. Okay, so they basically just fiddled with those two parameters and seeing what kind of magnetic field strength they get. And what they find is actually if you have relatively big blobs and you melt them quite quickly, you can get very, very strong magnetic field intensities. So they're basically just arguing these are the sorts of intensities we're seeing in the early paleomagnetic record. Maybe the origin of those is the melting of these titanium-rich blobs at the CMB. Quite a cool idea. I read this paper and actually had an undergraduate working with me at the time on trying to figure this out. And what we had established was that in order to generate these fields, you basically have to do something that has a very short time of dynamo generation. Okay, so we're dealing with hundreds of thousands of years here, but we know that we have paleomagnetic observations spanning 500 million years at least. And it really just made me feel a bit uncomfortable in the sense that surely there's no chance that one of these random quick events means that basically every Apollo sample we've picked up and measured has given us a strong field. Those should be really rare. Almost every sample that we pick up on the moon should be unmagnetized. And what we've seen is the opposite. Almost everything we've picked up is magnetized. There's something missing here. So we then basically ran with their idea and simulated a very similar dynamo generation mechanism. So basically what I'm showing you here is just the observational record. So these are the paleomagnetic observations between about 3.1 and 3.7 billion years ago, which is this period where we have these sustained high magnetic fields. But actually we can put them into fairly discrete time periods where we have an on measurement. So we have at least 5 times over this period of the lunar history where we're getting strong intensities. And if we allow titanium-rich material to sink occasionally to the core mantle boundary, and every time we allow a field to be generated until we get a layer with the same thickness that we see from seismic observations today, then you can get qualitatively a very similar looking record. Okay, so my brown signals here are just telling me basically how much material I'm accumulating at the core mantle boundary. So this is my maximum. So at this point, the dynamo will switch off. I've not got any more titanium-rich material to sink. But that actually does give me these periodic ons that look a bit like this. So you think, okay, no, maybe this does work. Maybe this is a reasonable way of thinking about how those strong intensities were generated. And we can come up with some simple observational constraints based on the paleomagnetic record that we can test. And we can then calculate a probability of this mechanism giving us our observations. So the first thing, we know that our dynamo has to be active for at least 588 million years. Okay, so I have to have titanium-rich material sinking for at least that long in order to get the record that I see. The second thing we can look at is the best constrained paleo intensity. So obviously lots of these have really, really big error bars that go all the way to 0. But the best constrained one is actually this guy here. And our lower limit is 53 microtesla. So based on that reasonably well constrained paleo intensity, the magnetic field we're generating has to at least hit that bottom error bar. Okay, so the weakest field our dynamo needs to be able to sustain is 53 microtesla. And then we make an assumption about how long the magnetic field will have to be active in order for a basaltic sample to cool and crystallize on the lunar surface and to capture a record of that magnetic field. This one's a bit arbitrary, but we just set it to 10 days, okay? So a basalt, if it's cooling down and acquiring magnetization, if it's seeing the same field for 10 days, it'll probably give you a fairly robust record, okay? So that's the minimum time that the dynamo has to be active for in one go. And then our dynamo has to be active for 7% of the total time period shown here. Okay, so if we basically take these paleo-intensities that are not within error of 0, so the only ones that we know are definitely on the fields, and we think about how much time they take up, then the dynamo has to be able to sustain a magnetic field for 7% of this history in order for us to capture these samples. So those are our constraints based on what we know about the paleomag. And then, sorry, this plot looks really scary. I promise it's not as bad as it first appears. I basically twiddled all the parameters, so how often I was dropping titanium-rich material, how big a blob of titanium-rich material I was dropping, how quickly it melted once it reached the core mantle boundary. I made all of those parameters basically as free as I possibly could. And these are the results of all the simulations telling me how long what proportion of time the dynamo is active for. So we have several spikes in events, and if we take that total time and then work out how long each of those events lasts for, that gives me a percentage of time the dynamo is active for. I work out the maximum magnetic field that was generated, so basically how big is my biggest spike in magnetic field generation. How long did the dynamo have spiky behavior for? So basically, how long is it until I run out of titanium-rich material? And then how long is my average melting time of these titanium-rich blobs once they reach the core mantle boundary? So I'm plotting up essentially how many of my 4 observational criteria all of my simulations reach if I let my simulations run over as much parameter space as I think is reasonable. And so actually what we find is all of them meet this criteria of having an average melting time of more than 10 days. That one's not a problem. We can easily do that. That's fine. So all of these blobs I'm showing here sit on this colour scale. That's not an issue. And then in order to meet our total dynamo duration, I have to exceed this red line. Okay, so I have to sit in this region. In order to exceed 53 microtesla, I need to sit in this region. And then in order to have a dynamo that is active more than 7% of the time, I have to sit in this yellow diamond at the top. Okay, so for the first 3 criteria, so a dynamo that is sustained for, sorry, my numbers have changed. It's I'm half revising this talk. 664 is the number you should trust, not this one. So I've got a dynamo that's sustained for the right amount of time. It exceeds my threshold of 53, and all of my colours are okay. So these points that sit in here are all meeting my first 3 criteria. They're all good. I can explain the paleomagnetic record based on those. But none of them explain having a dynamo that appears to be active for at least 77% of the time. None of them sit in this yellow diamond up here. So not a single one of my simulations can explain all 4 criteria that we're seeing from the observational record. And actually, if we calculate the probability of the best case simulation out of all of those giving us the observational record, it's a 1 × 10⁻⁷ chance that those samples the astronauts picked up and that we've measured would give us the paleomagnetic record that we see. So basically this doesn't work. And the reason that it doesn't work is because these events are really infrequent, right? They're not happening very often. You have big hundreds of million year time gaps between one of these titanium-rich diapir sinking, and they're melting very fast. So these events are really rare and they're really fleeting. The chances of actually seeing one of them is essentially impossible. So this can't be the answer. So that made me a bit sad and a bit disappointed. And I thought, okay, well, fine, that's not the answer then. We're back to square one. We still can't explain it. And then I was in the pub with an experimental petrologist in our department complaining to him about the fact that the moon was still broken and I still couldn't understand any of it. And he said, well, what's the composition of the samples that you're getting your positive paleo intensities in? Is there anything to do with what lithologies you're looking at? So I don't think anyone's ever thought about it that way, which kind of seemed mad in hindsight. So I then went and plotted up basically what rock type people had measured. Versus the paleo intensity they saw. And actually, all of these strong paleo intensities that we see are in basalt. People have measured anorthosites, they've measured breccias, they've measured all sorts of things, which will give you generally null paleo intensities. The only ones that give you these strong paleo intensities are the basalts. Ignore this troctolite, that's another problem child. That's very, very early in the lunar history, and that's probably actually just a genuine early thermal dynamo. So we're not considering that here, but all of these other ones that sit in this difficult part to explain are basalts. Okay, that's kind of interesting. Then the real clincher was I plotted up the titanium content of the basalts that have erupted on the lunar surface over time. And not only are they all basalts, but they all appear to be titanium-rich basalts, okay? And remember, it's titanium-rich material that we think is sinking to the core mantle boundary over time. And so I then just simply plotted the titanium content of each of those basalts versus the paleo intensity that it's recovered. And we actually see we get quite a nice correlation, okay? So the pink results here, so again, you can see on a histogram, all have systematically higher paleo intensities than our low titanium basalts that actually all are within error of 0. So we don't know if a single one of these has actually reported a true paleo intensity. Every study has given an upper limit because they're not very good paleomagnetic recorders. So this is interesting. Suddenly, we have a mechanism of generating very strong fields by sinking titanium-rich material to the core mantle boundary. And we have a real bias in the observational record that everything that has given us a strong field is from a titanium-rich sample. And again, we can plot this up with every time there has been a period of lunar volcanism and the composition of that volcanism, you can actually see that it's really, really tightly constrained in these regions of high titanium. Basaltic volcanism is when we're getting all of those strong intensities. So suddenly we're not looking at the whole of lunar history and looking at totally random events and thinking there's no way we're going to capture one of these snapshots. It's simply not possible. Actually, the snapshots are the exact times where the titanium-rich material is melting. Okay, so we have a huge bias in terms of the timings that we're actually getting samples from. So what we're now trying to propose, and I will leave it to you whether you buy this or not, is that we have this titanium-rich material that is sinking through the lunar mantle because it's dense, okay, so it's gravitationally unstable. Once it gets to the core mantle boundary, it's at different pressures and temperatures to where it would like to be. That causes it to melt. That melting draws heat out of the core, drives a short-lived dynamo, and at the same time, this melt comes to the surface, erupts, and the basalts crystallize and capture the magnetic field that was generated by the titanium-rich material melting. So actually, it all starts to make an awful lot more sense if the thing that is making the samples is also the thing that is driving the magnetic field. So this is why we are fortuitously sampling, massively oversampling these very, very short periods of time. So, have we solved the moon? Probably not. But I think we have come up with some very, very nice predictions that we can now go out and test. So if this mechanism has any legs, if it really works, then we now know every other lunar sample, if we measure it, we know what we should see. Okay, so we know for the lunar breccias and the lunar anorthosites, if we pick any of those to measure, we should see a null magnetic field because they're not anything to do with titanium-rich material melting. That shouldn't be giving us a signal. And with the lunar basalts, now we should be specifically picking the ones with very high titanium contents, and we should expect to see strong magnetic fields. And if they have a low titanium contents, I would say the jury is out as to whether we would expect to see a null paleo intensity or a weak paleo intensity. But I think we now know what we have to go out and test. And if this starts to then fit in and our predictions hold up, then I think we might have come a little bit closer to solving the moon. And we're also going to be massively helped by the upcoming Artemis missions. So NASA are planning to launch manned missions to the moon, starting again possibly as soon as 2026, but probably not. And I think this will resolve an awful lot of outstanding questions, because as soon as we have manned missions going back to the moon, it will allow us to take more in situ samples. So if they can go and get rocks that we know the latitude of, then rather than me having this one data point here, we can fill this whole thing in, and then we will be much more confident in whether the lunar magnetic field really is dipolar or not. We will have far more samples with better context. Hopefully they will send more geologists this time. And so then we can test our idea of the paleo intensities with rock type. Does that hold? We know the parts of the moon that are titanium rich on the surface. If we go and preferentially sample those, are we going to get an awful lot more rocks with strong paleo intensities? And also we can ground truth these magnetic anomaly maps, and we can see actually if you measure the magnetic field on the surface, does this hold up? And this is something that's been done for Mars relatively recently, and actually the story is totally different once you get close to the surface. So I think I'm optimistic in the next probably 15, 20 years, we might actually be able to answer some of these questions. But I think it's a fun problem to have thought about. Thank you very much for listening. I just want to thank all of my colleagues, including Jack Schmidt, the last man to walk on the moon. Anyway, I'll finish there. Thank you.
Oh, right. Thanks very much, Claire. That's a fascinating talk. And do you have some questions?
Have an unlimited number, so
Unlimited. You can have one. And then...
Well, it's more a comment. You're saying the moon is a slow rotator. I would argue with that. First of all, the general, there's all sorts of funky non-dimensional numbers they use for these plots, but the basic one is the
Mm-hmm.
And the Eckman number for the Earth might be 10 to the minus 14, and the moon might be 5 times 10 to the minus 12. That ain't a great deal of difference. And all of the numerical dynamos we have Eckman numbers, which are many orders of magnitude below that. So if you scale it in terms of rotation, much slower rotators. So a factor of 30 is not really making it slow. Even more if you think about past history when the moon would have been closer to the Earth because of the separation. So let's take the radius to an 1/8.
Yeah.
Which is certainly reasonable for an early formation, but that would mean the period would only be a quarter. So now we're down to a period of 8 days. And 1 day, 8 days, that's not a big difference when we look at orders of magnitude.
Yes, I tend to agree with you. I will counter you by saying I'm just going on what's been published in dynamo literature, because I think it's a local Rossby number of 0.2 is their threshold for when you go multipolar. And the Rossby number for the moon is much lower. So based on theory, they're placing it very much on the multipolar side. I can't justify whether that's reasonable or not. And actually, I think given Mercury as well, maybe there is an issue with thinking about that threshold. We did also think about the distance of the moon from the Earth and whether that would explain if you end up with strong fields and very dipolar, and then as it moves away, it becomes multipolar. But I think it moves away so early in its history, actually, it makes no difference. But it's, yeah. But I would actually be quite happy if it is okay based on all the dynamo parameters that it can be dipolar. I think that would solve a lot of issues, but I don't know if that's it. So.
The other thing on the dynamo is when we start worrying about multipolar dynamo, what they mean is multipolar if you look at the surface of the dynamo. So
Right.
we're at factor 7 up.
Yes.
So even if it's multipolar, it's going to look dipolar.
Yes, that's very true. Yes. So it might actually be, if you were at the core mantle boundary, it still would look multipolar. Yeah. So maybe it's not such a problem to explain after all. Yeah.
It's a nice problem to think about.
Yeah.
But I don't think it's the numerical dynamists do tend to love to come up with this great statements of what's going on when their dynamos have absolutely nothing to do with actually what the planet is doing. So I think that they are on weaker grounds than the observations.
Good. That's what I like to hear.
Someone else take this, or I'll just ask more questions for it. I'll get catch Claire afterwards.
Stand silence, please.
I
Someone say.
will weigh in on that. The option that just, I mean, I guess this kind of supports what they're saying really, but I mean, using the local Crosby number in particular, what we're talking about there is giving the role to inertia, then with 2, and then that influencing the magnetic momentum, I think, in producing then this having an influence on the shape of the field. Now, basically, if that argument's right, it's rapidly going out of fashion, because then the Earth, the geodynamo should never reverse, right? Because it's obviously the inertia is not important, is not thought to be important, right, in the force balance for the geodynamo, and it's only inertia that is producing these reversals, right? And so there is probably, I think that could probably all be rewritten as it apparently needs to be, right? So it's an accurate.
Yes, yeah.
So, I think that's good. That'll be good. People online with this.
I just had a question about the crater cross section that you drew, and you said that it was had been significant mass wasting,
Yeah.
which I would guess means material goes from the start to the bottom of the crater.
Yeah.
But the way you drew it, it looked more like a truncation surface where everything had just gone somewhere else.
Yes.
There was nothing at the bottom that had come from the sides in that cross section.
No, and it is so it's a cartoon that I lifted from a paper, and I think you're absolutely right. And I've always struggled with why you don't have a great big pile of rubble in the bottom. And I guess the problem is, from the images of that crater, it does just look totally smooth. So it looks like there has been mass wasting, but I actually don't understand really quite where that material has disappeared off to, which is a bit of a problem. I don't mind the idea that you're exposing kind of in situ material in the walls, but yeah, I think it's an issue why it's not, when you can see it in the middle. And I don't have a good answer for why the morphology doesn't kind of look like that.
Oh, cool, good, thank you. Another question.
Yeah, another question that doesn't make any sense for the moon.
Yeah, I can be bad on this one. Titanium. Is it lithophile or siderophile?
Oh, that is a good question. Is titanium lithophile or siderophile? I don't actually know. Does anyone in the room? Yeah, in terms of whether it's actually going to end up going into the core, I would guess it can't be that siderophile, because otherwise it would have ended up in the core in the first place. Would be mine. And I mean, there are definitely. Yeah. I think it can't be that siderophile, because otherwise, because there definitely are, you get loads of ilmenite in the basalts, so it definitely is not all being sequestered into the core when you differentiate. But actually, how lithophile versus siderophile is, I don't know. But yes, I guess you're absolutely right. But if it is even moderately siderophile,
I asked the geology question. Definitely not right.
Yeah, you're right to raise it as something that we should think about. Yes.
I think it, but of course that's only
And also it's under much more reducing conditions than Earth, which also is a problem for how it behaves.
So in titanium, you kind of plot it as, it's rotile, right? TiO2, but is that how it's been, is that how it appears, or does it go in with the ion side?
Well, we don't have any magnetite because there's no oxygen or ellipses, so everything, all the carriers are camosites with all metallic ion. But yeah, I think ilmenite is the main titanium bearing phase, and there's been a lot of petrology papers on kind of the ilmenite cumulates. So yeah, there's definitely, I think it's kind of inarguable that there are very titanium rich basalts. How they're generated is less well known, but they're a good kind of case for what's causing that mush there.
Questions not being near as intelligent as the rest of them, so please excuse me on that one. In much earlier on in the bit, you ended up disproving yourself about, you mentioned that they cooling on the order of 10 days. Question about that, and then sort of follow on. But is that as in like the material you find at the surface, how quickly you were estimating that was cooling?
Yeah, it's basically just a kind of order of magnitude, how quickly a basalt might cool on the lunar surface, and saying that's a lower limit. It's got to be at least that long. Yes, so it's a very approximate. This is what the cooling rate looks like. Let's scale that up to how long it will take to go through it.
So, yeah, because I was wasn't sure with how quickly something would cool in what's, you know, in vacuum. I don't know, because obviously you don't have like convective. Maybe I can't remember the words today. But yeah,
It's hard to say.
Take difference really. But yeah, but if that was the lower limit.
Yeah,
so
so I
it has to
guess-
be greater than.
Yes, because we do, you do get lots of lunar glasses as well. So we do see lots of kind of like spatter glasses coating things. So there are really fast cooled samples as well. But these are actually quite coarsely crystalline. So probably they're not quite getting to the surface. I would imagine they're cooling kind of within a stack of lavas that's already there, which is slowing them down. Because I think you're right, if they just erupted onto the surface of the moon, you imagine they would cool extremely quickly.
Well, I was trying to work in my head whether it would be extremely quickly or weirdly slowly because there isn't any air to current it away. But that's from my lack of knowledge.
No, I think it's a good question though. Yeah, it's something I have. It's a very approximate kind of arm wavy. I think this rate is about right, but actually it'll be interesting to know because obviously I don't look at fresh basalts from Earth, so I
Frequently test it, just get something very hot in the vacuum chamber.
yeah.
Thank
Thank you.
you, Claire. Thank you for the great talk. I just wondering for the oriented sample, how to evaluate or exclude the impact of magnetic field, the influence of the impact magnetic field.
Oh, so the idea that rather than it being generated by a dynamo, the magnetic field is actually impact generated. Is that what you're asking? Like how can we prove it's not generated? Yeah. So in the impact cases, let's see if I can find it very quickly. Yes, so there are basically two impact cases that have been proposed. One is this antipodal one, where you basically have plasma that's magnetized coming directly out of the antipode. So then you would expect the inclination to be really steep. If it was impact generated, it doesn't matter where you are, you would expect to get something that's pointing basically out of the surface. And then the other idea is cometary impact, which is essentially kind of the same idea, but backwards, where they proposed you would have plasma wrapping around the lunar surface, in which case you would expect it to be flat. So the fact we're seeing something between the two, I think rules out both. And also impacts, the magnetic fields you generate are incredibly short-lived. So yeah, so actually by the time your basalt's cooled, it probably wouldn't see it.
So can you find any large impacts create within the antipode of the sample result? Antipode.
I guess you could. The problem is there's so many craters, right? We know that every crater has ever hit the moon, so that kind of implies that if it worked, you would get an antipode everywhere. Yeah, so I think we can quite confidently rule out impact magnetism. Yeah.
Okay, thank you very much.
I'll finish with a very quick fun one now. So, you know, you've got this nice restoration to the paleo horizontal. What is there any scope with current samples that will, you know, maybe there could be a field trip in the future, right? For a whole test. So you've got multiple samples with different orientations and store them in the other group.
Yeah, that's I think there is a chance. Actually, it's annoying because mostly what the astronauts picked up was just regolith, because I guess it's easy to sample. But you can see in some of the photos behind them are like cliffs of amazing kind of plain looking features, and I'm sure some of those are not perfectly flat. So I would say there's probably a reasonable chance of doing that. Yeah, which will probably again cause more problems than.
Okay, thank you very much.